Very good morning. Welcome you all to the NPTEL course on Advanced Distribution System Analysis and Operation. Today we'll be talking about impacts of distribution energy resources, or that is so-called DRs, on distribution grids. So we'll focus on how distributed energy resources impact my distribution grid after their integration. Now, distributed energy resources significantly impact distribution grid, bringing both benefits and challenges. So, always we experience bit of merits because of DR integration, and it is not free from challenges associated too. Reduction in greenhouse gas emission due to power generation. So, in the past we used to generate energy mostly from actually thermal, and probably through renewable energy those gas emissions can be limited or reduced. So, low greenhouse gas emission due to use of clean energy resources, that is DRs, which can help me not to have excess emission. A study has shown that a 2 kilowatt photovoltaic system in Montana avoids 0.68 pounds of NOx and 3643 pounds of carbon dioxide emission, equivalent to driving 4,553 miles of or CO2 absorption of 1 acres of tree in a year. What does it mean? It very clearly tells us that having a renewable energy, the pollution due to NOx and COX can easily be reduced. Furthermore, another study has revealed that supplying 1 million homes with solar energy would cut carbon dioxide emission by 4.3 million tons annually, equal to removing 800,000 cars from the road. Imagine the consequences, imagine the impact. So, it is very loud and clear that we have to move towards distributed energy resources to avoid generation of CO2 and NOx. Now, that can also indirectly reduce the health damage. So, DG is capable of achieving this goal in two ways. The value of reducing the reliance on the central grid enables less power losses, and hence less power is produced from the conventional plants. The pattern of emission from outdoor or airborne pollutants such as NOx and SO2 and other from clean distributed generations units are less hazardous than emission of the conventional plants that DG replaces. Due to these two major factors, the quality of air is being conserved from man-made pollutants, which in turn means reduction in health damage. Now, how can we improve the grid resilience and reliability due to DR integration? So, as you could see, there are localized generations where DR such as rooftop solar PV, small wind turbines and battery storage systems provides power close to the demand centers and reducing dependency on centralized power plants. Redundancy and backup power, the battery energy storage and hybrid DRs systems act upon power backup during emergencies. Microgrid capabilities, the DRs enables microgrid operation which can continue supplying power even when the main grid experiences outages. Black start capability, some DRs especially battery storage and combined heat and power systems can provide black starts capability to help restore power after an outage. So, after having integration of DRs, we can have localized generation that can help, because in a distribution system when you locally inject some source, that will not only enhance the voltage capability at that end node, however the power being drawn from the transmission system or high voltage distribution system to the consumer end will now be reduced, and because the power flow is reduced and hence indirectly the system loss also will be significantly reduced. So, that is why the integration of DR is going to not only help on reducing the carbon, sulfur dioxide as well as NOx, but it can also reduce my system losses. Now, improved grid resilience and reliability, there are few practical examples. During Hurricane Dorian 2019, it has been realized that what kind of disaster it has occurred. And similarly in California wildfires, where during California wildfires, generator powered microgrids restored electricity, which is a significant achievement, because whenever there is a distribution network get disintegrated from the main system, probably the local system can only help you to survive. So that is why we always believe that the grid resilience and reliability is possible through microgrid integration, distributed energy resource integration in my distribution systems. Now, reduction in transmission distribution losses. Now, the decentralized generation, since DRs generate power closer to the consumers, as I have explained, the losses will significantly reduce. Now, the peak load saving by supplying local demand, DRs prevent overloading of distribution feeders and transformers, further minimizing technical losses. So, your transformer loading will be significantly reduced once you are locally generating and engaging them to cater the local loads. And the lower current flow, as I told you, the grid component will experience lower current flow because you are feeding few amperes of current from the local consumers through DR integrations. Now, what kind of voltage support and power quality improvement takes place? Because we can have smart inverters for voltage regulation, that means advanced distributed energy resources. Inverters can provide voltage support by injecting or absorbing reactive power, that is popularly known as volt var control. It also provides frequency support. Some DRs, particularly energy storage systems, can respond to frequency fluctuations and stabilize the grid. Now, reduction of voltage fluctuations. When properly controlled, DRs reduce voltage sags and swells, which improves overall power quality. Power factor improvement. DRs can correct poor power factor by supplying local reactive power, reducing stress on grid infrastructure. So, unlimited benefits due to DR integration. I mean, voltage fluctuation management as well as power factor correction is possible through DR integrations. Now, what about peak load reduction and deferral of infrastructure investment? This is a very, very important concept. What do you mean by deferral of infrastructure investment? Means today, imagine there is a transformer which is close to overloading. And if you connect extra load, you have a substation, loads are connected. If you put on adding loads, then the transformer is not going to cater. So, what we need to do, the distribution company, the DISCOM, has to replace most of their old transformers or replace the substations or put an additional transformer to cater the new customers or consumers. And can we avoid such investment due to DR integration become a question. So, battery energy storage system. So, storage systems charge during off peak hours and discharge during peak demand, which helps the load curve to be flattered. So, that means the peak valley now can be reduced little bit due to battery energy storage. Now, the next one is demand response program, where the controllable distributed energy resources can perhaps actually shift the electricity from the peak hours to off peak hours. Now, reduction in capacity expansion cost, that is, utilities can defer its investment in expansive substations, upgrade the transformers and the replacement, and the new transmission lines can be avoided. Now, enhance utilization of existing infrastructure, that is smoother load profiles, reduce wear and tear on grid components, extending asset lifespan is possible. And finally, the peak load reduction and deferral of infrastructure investment is possible through appropriate control mechanism and DR integrations. What are the challenges? We have all discussed the benefits as of now. Now, the challenges associated with DR integration, the first one is voltage unbalance. That is, uncoordinated installation of DRs, especially on single phase residential connections, can lead to voltage imbalance in a three-phase distribution system. This imbalance arises when one phase receives significantly more power injection than the other. According to NSI C84.1, the voltage unbalance should remain under 3%, and which is calculated through this way, the following formula, that is maximum deviation from average phase voltage upon the average phase voltage must be less than 0.03, that is must be less than 3%. All right. So, maximum deviation from average phase voltage upon the average phase voltage must be less than 3%. So, we need to assure that is not going to increase. Now, in case of line overloading, uneven power distribution among the phases can also result in higher power losses, and potentially it may create line overloading. Now, what about the reverse power flow? As you all know, the moment you connect a DR to the main grid, now previously the power is to come through this way, right, if there is a consumer. But because of DR, there could be a reverse power flow. Am I right? So, the grid to load and the DR to the main grid, the feeder may now carry power in a reverse direction compared to the previous case where the load is being catered from the main grid only. Now, there are two different challenges. For example, if I connect a load here, now if the DR source current is too high, so that which is more than the load requirement, then probably it will start flowing this way. So, previously it was coming through this way, and now it can also go in the reverse direction. So, reverse power flow, present network equipments are capable to handle only unidirectional power flow. So, currently all the devices are capable of carrying unidirectional power flows. Hence, mal-operation may be possible due to reverse power flow. So, instead of from main grid to load, now it is carrying power from actually DR to the main grid. So, main grid is now receiving power from the DRs instead of providing to the load customers. Now, one more important challenge is related to your protection, that is mal-operation of overcurrent relay. The increase in fault current due to PV integration may interface with the overcurrent protection of the conventional distribution grid. So, as you could see, with and without DR, now if there is a fault, as you could see, now the fault current from the main grid is seen through this red line, but because of the DR, you will experience another current. So, that leads to false tripping and outage of healthy feeder, which is not even a defaulter. So, because of DR, the system may experience false tripping, which is not needed. Now, in case of underreach, the relay at the substation may underreach as fault current seen by the relay is reduced due to contribution from the PV system. So, whatever the main grid current you see, now you also get some DR input here. So, the fault current seen by the relay is reduced due to contribution from the PV system. DR integration challenges, as we all know, one is voltage regulation, line overloading, reverse power flow, overcurrent relay, mal-operation. What are the solutions? DR hosting capacity investigation. How much DR penetration is allowed into the distribution circuit without violating the system constraints? Now, today, as I told you, when you integrate DRs into your system, what would be its limit? Can I go for 10% injection, 40% injection, or maybe 5 batteries, or maybe 20% of PV? All those solutions that need to be identified. So, DR hosting capacity investigation will help you to be free from majority of the issues and challenges being associated with DR integrations. So, let us get into DR hosting capacity assessment. Now, what do you understand by DR hosting capacity assessment, that is HCA? Is the process of determining the maximum amount of distributed energy resources such as solar PV, wind and battery storage that can be accommodated in a distribution network without violating operational constraints. So, what we are talking here, how much of PV, how how much of energy storage need to be connected in my distribution system so that the distribution network is not violating its operational constraints. DR deployment types, utility owned DRs, large capacity connected to high voltage level, mostly concentrated in few locations. Customer owned DRs, smaller capacity connected to low voltage level, distributed all over the network. And you will be happy to know at IIT Roorkee distribution network, not only we have actually 2.7 megawatt of PV at 35 different locations, but also we do have two storage connected at two different locations of the campus. Methods. There are four different methods to calculate the hosting capacity. One is snapshot or static hosting capacity assessment. The second one is known as time series hosting capacity assessment. The third one is stochastic hosting capacity assessment. And the fourth one is optimization based hosting capacity assessment. What are the constraints we are considering? Voltage limit, thermal capacity of lines and transformers, protection, coordination and reliability, and power qualities. So, we will see during next 10 to 15 minutes how those hosting capacity assessments can help us for the distribution system to be free from thermal capacity violation, voltage limit violation, protection coordination violation, and power quality violation. Let us focus on snapshot or static hosting capacity assessment. It is a power flow based method that evaluates the maximum DR capacity a distribution network can accommodate at a single point in time. It typically considers worst case operating condition such as maximum load as well as case 2, which is of minimum loads. So, hosting capacity HC is the minimum of the hosting capacity of case 1 as well as hosting capacity of case 2. So, we will determine the hosting capacity during maximum loading condition, we will determine the hosting capacity during minimum loading conditions, and then we will take the minimum of both to determine the overall hosting capacity of the network. Now, what are the key features here, which is quite fast, computationally efficient, which uses power flow analysis to check network constraints and provide a first level estimation of hosting capacity. But unfortunately, it does not account for time varying nature of DRs, how they are behaving over a period of time, and it also ignores uncertainties in solar, wind as well as the demand profiles. Let us understand the next method, that is snapshot or static hosting capacity assessment. Methodology for static hosting capacity assessment. Select a snapshot condition, peak load scenario as well as minimum load scenario. It performs load flow analysis using some method or tools. Check for operational constraints, that is the voltage must be below its maximum and more than its minimum, and the thermal limit must be less than or equal to its maximum capacity. So, then we can determine the hosting capacity by gradually increase the DR penetration until a violation occurs. Means we can start with 0.1 per unit, 0.2 per unit, 0.3 per unit. Slowly we can increase the DR penetration till the system violates its voltage or thermal limits. The maximum permissible DR is the hosting capacity of the system. Now, we can simply have a case study we have demonstrated for IEEE 33 bus system. The voltage level is 12.66 kV, total active power load is 3715 kilowatt, total reactive power load is 2300 kVAr, and it is purely a radial system. Now, it has been observed from the study produced by other researchers that the V minimum is 0.9, V maximum is 1.1 per unit, and S max, which is 6 megawatt, and the substation transformer rating is 6 MeV. One solar based DR is integrated at bus number 18. Now, this is the data for IEEE. The previous one, as you could see, 33 bus system, network architecture, and these are the values. We can find all your R and X between the buses, the loads are known to you, and the voltage level, which is once again 12.66 kV as I discussed earlier, and the total active power load is 3715 kilowatt, and the reactive power load is 2300 kVAr. Now, when it has been simulated, you can see the simulated voltage profile between bus number 1 to 33. The upper limit is considered to be 1.1 per unit, and the lower limit, which is going to be zero 0.9 per unit. So, it is expected everything has to be like this. But voltage at bus number 18 is exceeding 1.1 per unit. Why it is happening? All of you please have a look here. So, at this bus number 18, now we are injecting extra power through PV. So, when you are injecting extra power through PV, so that means the voltage experience bus number 18, as you could see, is slightly high now. So, the voltage at bus 18 exceeds 1.1 per unit in this case for 3 megawatt of penetration. So, the maximum DG capacity can be added is 3 megawatt. So, that means the moment you inject more than 3 megawatt, the voltage violation occurs, and hence we recommend that the hosting capacity for the network for DG integration of PV will be equal or less than 3 megawatt. Is it clear? Now, these are the simulation results, active power intake, apparent power intake, and the transformer rating of 6 MVA. Active power intake from the upper grid is gradually reducing with DR capacity. Apparent power is also reducing and it is not crossing transformer ratings. We can also see the simulation results, the change in voltage with DR capacity at bus number 18. If you keep on injecting, as you could see, 0 0.51, 1.52 to 0.53, 3.5. The moment you are making 3.5, it is crossing 10% margin, and hence we have to stop at 3 megawatt penetration at voltage at bus number 18. The voltage at bus 18 is increasing with DR capacity. When the DR capacity crosses 3 megawatt, the bus 18 experiences a voltage limit violation. So, with this observation, we can say the hosting capacity is 3 megawatt at maximum loading conditions. Now, we can go with minimum load conditions, and we can see the similar kind of scenarios. So, where the lower limit is given as 0.95, the maximum is going to be 1.1, and the voltage at bus 18 exceeds 1.1 per unit when it is crossing 2 megawatt. Very interesting. So, what does it mean? The voltage at bus 18 exceeds 1.1 per unit in the case for 2 megawatt of penetration. So, maximum DG capacity can be added is my 2 megawatt, all right. So, there is a small correction. So, this can be my 0.9 per unit. Simulation results, you can see that active power intake from upper grid is negative after DR capacity is greater than 1 megawatt. Apparent power is reducing up to 0.5 megawatt, and after that it starts increasing. However, apparent power has not crossed the transformer limit of 6 megawatt. So, the conclusion here, as you could see, the moment we come from actually 0 0.51, 1.52, it is within limit. The moment you inject 2.5 megawatt, it is violating my 10% limit. So, what does it mean? In the first case, maximum loading condition, we found it is 3 megawatt. In case of minimum load condition, we found it is 2 megawatt. So, the minimum of 3 megawatt and the 2 megawatt is 2 megawatt means the hosting capacity is 2 megawatt will be acceptable to the system either in maximum loading operational conditions or during the minimum loading operational condition. So, with this observation, the hosting capacity is not 3 megawatt, but it is 2 megawatt at minimum load. The third method, which is very interesting, time series hosting capacity assessment. Time series hosting capacity assessment, that is TSHCA, evaluates the maximum distributed energy resources DR penetration that a distribution network can accommodate over an extended period, considering the time varying nature of number 1, load demand fluctuations, DR generation variations, grid conditions. This method provides a more realistic assessment than static HCA, and it considers the actual operation of the grid over different time intervals. So, perhaps this considered bit of dynamism in the system, that is 1 minute interval, 15 minutes interval and 1 hour interval, how the scenario is going to change, not those extreme minimum maximum conditions. So, what are the key features? Captures variations in load, generation, and grid conditions. And it is quite more accurate for your hosting capacity analysis, computationally extremely intensive, and it requires historical or forecasted time series data. Now, finally, the stochastic hosting capacity assessment. The stochastic hosting capacity assessment SHCA is a probabilistic approach to evaluate how much distributed energy resources DRs can be integrated into a distribution network under uncertainty, because anything can happen. The energy resources may change, the load consumers may behave differently. So, the DR generation may create uncertainty, load demand may create uncertainty, and DR placement and size, may also behave differently with different weather conditions from time to time. Instead of a single deterministic result, SHCA estimate the range or the probability distribution of the hosting capacity. Instead of very specific, the 2 megawatt at bus number 18 is acceptable, it can give you overall range or a probability distribution characteristic how this hosting capacity must look like. So, what are the key features of stochastic SCA? Captures uncertainty in DR and load profiles, accounts for spatial and temporal variability, provides probabilistic matrices, whereas computationally it is very intensive and complicated, requires large data sets and statistical modelings. Optimization based hosting capacity assessment. Optimization based hosting capacity assessment OBHCA uses mathematical optimization technique to determine the maximum DR capacity that can be integrated into a distribution network while satisfying all grid constraints. Unlike other methods that incrementally test DR levels, OBHCA formulates an optimization problem to directly maximize hosting capacity or minimize its cost, subject to physical and operational constraints. The key features of OBHCA is to provide a precise maximum DR capacity, can include network upgrades, control actions, and cost minimization, suitable for multi-objective planning, but unfortunately it requires complex modeling and solver tools and may not directly handle uncertainty unless extended to robust or stochastic formulations. So, with this we are coming to an end of today's lecture. The very important part of today's lecture is the hosting capacity, means how much of PV integration or a wind integration at a particular bus is possible without violating your voltage or thermal limits. Thank you very much. Bye bye.